Generally speaking, fusion is a reaction between two atoms which fuse together to form a larger and heavier atom, as well as neutrons and energy. As far as scientists know, fusion only occurs naturally inside of stars such as the Sun. Fusion occurs by having particles heat up to millions of degrees Kelvin. This insanely high temperature causes the electrons of the atom to be stripped away, resulting in positively charged ions and negatively charged electrons floating around freely, forming a plasma. Since the ions are positively charged, they repel when they are near one another. This repulsive force of charges, known as the Coulomb force, needs to be overcome for fusion to occur. The amount of kinetic energy needed for the ions to get close enough to fuse is called the Coulomb barrier. The strong force is the force which binds the protons to the neutrons and only becomes active once this barrier is passed. There are two factors which strongly contribute to this event, which is temperature and pressure. The kinetic energy of the ions increases proportionally to temperature, and as the pressure increases, a collision is more likely to occur between the ions. Once two ions collide with enough kinetic energy, fusion occurs, resulting in a heavier atom and free neutrons. These free neutrons and atoms' combination of masses is less than the combined mass of the original ions which fused together. This phenomena is described by Einstein's most famous equation, E equals mc squared, showing how energy and mass can be interchanged. In fusion reactions, the loss of mass in the resulting heavier atom and free neutrons has been converted to energy. Fusion is most likely to occur with atoms lighter than iron-56, where the reaction is exothermic. Any atoms heavier than iron-56 result in endothermic reactions, which require an external source of energy, which is why atoms lighter than iron-56 are more likely to fuse and atoms heavier are more likely to split. The most common fusion reaction is between deuterium and tritium, which are both isotopes of hydrogen.
All stars are made up of mostly hydrogen and helium. A star's core burns at approximately 15.6 million Kelvin and is 10 times more dense than lead. At this density, one may question why a star's core isn't solid. Instead, it's made up of a plasma because of the insanely high temperature. The Sun, being 99.8% of the mass in our solar system, is an ideal environment for fusion to occur. Stars have an ample amount of hydrogen, and with their strong gravitational fields, they create immense pressure. This great pressure contains the plasma at the star's core, and the high temperature causes the nuclei at the core to fuse. Every second, the Sun fuses 700 billion tons of hydrogen to produce 695 billion tons of helium. The remaining 5 billion tons has been converted to energy, equivalent to 80 billion 50 megaton nuclear bombs. That's enough nuclear bombs to bombard the entire surface of the Earth over 600,000 times a second. Research into fusion power began in the 1940s, and currently there is no design that has produced more energy than it has consumed. There are two main types of reactors, ones that use magnetic confinement and those that use inertial confinement. Magnetic confinement fusion uses powerful magnetic fields to hold the hot plasma in place, which fuels the reaction. Inertial confinement works by heating and compressing a fuel target until ignition, usually a pellet that contains deuterium and tritium. The first three systems which attempted to produce fusion included the Z-pinch, the stellarator, and the magnetic mirror, all of which used magnetic confinement. Each machine has its own flaws, but have led scientists to the creation of the tokamak, one of today's leading fusion designs. The tokamak is in the shape of a torus, and uses a combination of toroidal and poloidal magnetic fields. The toroidal magnetic field takes on the shape of a ring, which the plasma will flow around, while the poloidal magnetic field will move in circles around the plasma. Using magnetic fields is an effective way to confine the plasma because plasma is a gas of ionized atoms and electrons. This means that they have a combination of both negative and positive charges, and therefore can be deflected and confined by a magnetic field. Even with the use of magnetic fields, the plasma over time will accumulate instabilities, which make the fusion confinement very difficult and fusion impossible. This results in the fusion reaction taking place in the tokamak for only a few seconds. Therefore, the tokamak containment chamber is only exposed to the extreme conditions for a short time. The second leading design uses inertial confinement by lasers. This process pulses powerful laser beams of energies of about 1 million joules lasting about a millionth of a second onto a small spherical pellet that contains only micrograms of deuterium and tritium. This focusing of lasers causes the outer layer of the pellet to rapidly heat up and explode. The remaining portion of the pellet is driven inward and compressed to about 10,000 times its normal density. This compression of the fuel inside the pellet forms a shock wave which further heats up the fuel in the very center, resulting in fusion. The energy resulting from this fusion reaction then heats up the surrounding fuel, and if the heating is strong enough, then the surroundings could also undergo fusion. This chain reaction is called ignition and is the goal for inertial confinement. It's called inertial confinement because the plasma is confined by the inertia of its own mass.
The tokamak design has three key parameters which will result in producing more energy than the amount of energy put in. These parameters include the temperature of the plasma, the density of the atoms, and the energy confinement time, meaning if the heat is turned off, how long does it take the plasma to cool down? Issues involving inertial confinement include the delivery of the energy to the fuel, symmetrically exploding the outer layer of the fuel, and having the fuel compress evenly. The energy required to heat the plasma is proportional to the density of the ions N, and the rate of fusion is proportional to N squared. If tau is the confinement time, the output of energy is proportional to N squared times tau. If the output energy is to become greater than the input energy, we must have C1 times N squared times tau is greater than C2 times N, where C1 and C2 are constants. N times tau must be greater than 10 to the power of 20 seconds times particles over meters cubed. If Lawson's criterion is met, then the reactor will just break even in the amount of energy output compared to the input energy. For reactors to be practical, the output energy must become much greater.
When nuclear fusion is finally achieved, the world can expect limitless power with abundant fuel. That means humanity can look forward to a power supply to last generations. However, fuel is not so abundant. Fusion requires equal parts deuterium and tritium to work, and while deuterium exists at 155.76 parts per million in our oceans, it can simply be extracted from seawater. Obtaining tritium is much harder. Tritium is exceedingly rare to find on Earth, with only about 20 kilograms of it in existence, most of it being found in the world's nuclear warheads. With tritium being so rare and expensive, leading scientists have proposed using helium-3, an isotope of helium with only one neutron. While it's also hard to find on Earth, the surface of the Moon is covered in it. Without the protective atmosphere of Earth, the Moon is left to be bombarded by solar winds, which carry atoms of helium-3 through the vacuum of space until they collide with the Moon's surface. It has been theorized that it might be easier to mine this helium rather than synthesize it in lab. Helium-3 has the upside that when it fuses, the surrounding materials don't become irradiated. However, it needs higher temperatures to achieve